Hello guys, and welcome back to another video. Today we're starting a new video series on differential equations, and before starting with the course, I wanted to thank my teacher for giving me this amazing book on differential equations, and I'm going to follow this book to record these lessons, these videos. And I cannot tell you the name of the book because it's not an English textbook. And apart from that, I think it's time to start looking at differential equations. But before talking about differential equations and solving differential equations, we need to ask the question, what is a differential equation in the first place? Well, before answering that, let's think about normal equations. We're all familiar with equations. For example, let's take the equation x squared minus 4 equals 0. What does this equation mean? Well, we need to find a number that placed into this equation instead of x, so x is the number we have to find, gives 0 on the left hand side, so 0 equals 0. So it satisfies the equation. And we know how to solve these equations. Equations can have one solution that is a number, two solutions, so two numbers satisfy the equation. In this case, there are two solutions. We have x equals 2 or x equals 2 minus 2, because 2 squared equals 4, 4 minus 4 is 0, so 0 equals 0 is true. And x equals minus 2 squared is plus 4, minus 4 equals 0. So as you can see, this equation is satisfied by two numbers. Differential equations are similar, but instead of having a number, we have a function. And there is a more general class of equations involving differential equations. They're called functional equations. And I'll tell you what a functional equation is. Basically, you need to find a function, and that function is the solution to the equation. So we'll start with a geometric example to see a differential equation and get an idea of why they're important and how to use them, why they're important. So let's take a function. This is our xy plane, and we have a function that goes like this. For now, it's not important, the behavior of the function, or at least it is important, but I've drawn a random function because I don't know the solution yet. So, for example, I want to find a function, not this function, because this function doesn't satisfy the equation. I've drawn this function simply as an example, but it's not a solution to the equation. Suppose we want to find a function which slope equals 2 times, which slope at some point equals 2 times the coordinates of that point. For example, this is the x coordinate of the function, this is the y coordinate of the function, and I want to find a function which slope at this point, and we know that the slope at that point is the derivative of the function at that particular point, equals 2 times the product of the coordinates. I set up this problem because I want to find a function that satisfies this equation. We can also write this in the following way. It's a simpler notation. I love Leibniz notation, but this is also convenient. Y prime equals 2xy. That's a differential equation. So we need to find a function that, substituting this equation, makes what is on the left-hand side equal to the right-hand side of the equation. We're not going into the details of how to solve a differential equation yet, because it takes some time, but I'm going to give you the solution to this equation. So we're not studying how to solve a differential equation yet, but I'm giving you a solution to this equation. And we're going to see whether this function satisfies this equation. So we first need to compute its derivative, so y prime equals 2. c times e to the x squared, where c is just an arbitrary constant, times the derivative of the exponent, so 2x, and this equals 2x times c e to the x squared. But now look at this. This simply equals to y. It's the original function. So this equals to 2xy. And indeed, y prime equals to 2xy. Now notice something very interesting. This equation is not unique because we have an arbitrary constant. And this is true for any arbitrary constant. It could be -5, it could be 10, it could be 10,000, the equation still works. This is still a solution to our equation. So there are an infinite amount of solutions to this equation, and basically the solution is both a function of x and a function of c, because it has two kind of independent variables. Even though we're differentiating with respect to x, there's this variable here that gives us an infinite amount of functions, c times e to the x squared. And all these functions fill the entire plane. Now, this is called the general solution to the differential equation. General because it's general for any c. These are all the solutions to this differential equation have the following form. But what if we want to find a specific solution? So we want to determine this constant. How can we do that? For example, we want to find the solution to this equation that goes through the point in the plane x equals 1, y equals 1. Is there a way to do that? Well, let's see. Firstly, let's substitute these two numbers into our function. So y equals 1 equals to c e to the x, so 1 squared. 1 squared equals 1, e to the 1 equals 1. Therefore, c times e equals 1, and c equals 1 over e, or e to the minus 1. We can substitute this into our equation, and we get y equals e to the minus 1 e to the x squared, so y equals to e to the x squared minus 1. Now, this is also a solution to our differential equation. If you substitute this, you can check it if you want to, into the differential equation, you get that these satisfy the differential equation. But this is not general because there's only one independent variable, there are no parameters involved, and this one is a particular solution to the differential equation. So this is the general solution. All solutions to this have this form, and this is a particular solution. In particular, the solution that goes through the point 1, 1 in the xy plane. So that's an example of differential equations. Now we're going to see another example. So just give me a couple of seconds to look at the example because I wrote it here. So the example is, we have this differential equation, 1 over the square root of y, where y is the function, dy by dx. And this equals to 1. Again, we're not solving the differential equation today, but we're just checking whether the solution satisfies the equation. And the solution to this differential equation, the general solution, is x plus c squared. Remember, x independent variable, c an arbitrary constant. So let's see whether it works. Now, 1 over the square root of y. You might be tempted to write down x plus c, but the square root of something squared is always positive. And x plus c isn't always positive. It could be also negative. So we need to put the absolute value of x plus c. Be very careful about the domain of functions and absolute values, square root. This is very, very important. Otherwise, you get stuck at some point because something doesn't work. Then we have dy by dx. Now let's compute the derivative. Y prime, that is dy by dx, equals to, chain rule, 2 times x plus c times 1. The derivative of the inside function is 1. Therefore, we can replace this by... Sorry, I forgot a 2 in front of this. Sorry. There should be a 2 here in order for this to be a solution to the differential equation. So we also need to put a 2 here, and we need to multiply by the derivative. So we have 2 times x plus c, and this equals 1, or at least it should be if this is a solution. Now, can we simplify x plus c and x plus c? Here we have an absolute value, here we have normal parentheses. So we can, but only if it satisfies a condition. The condition is that x plus c must be greater than 0, because if this is greater than 0, then the absolute value tells us that this is simply x plus c, because if this were negative, then this would have been minus x plus c. So if this condition is satisfied, so x plus c is indeed greater than 0, we can simplify x plus c and x plus c, and of course greater and not greater or equal to, otherwise 0 in the denominator wouldn't work. We can simplify the 2 and 2, and we get 1 equals 1. So this differential equation is satisfied for this function, but we also need to specify the domain, and this is a very important point, because the function is not only how you write the algebraic expression for the function, it's also the domain of the function. So a very important point is to specify the domain, and the domain is that x has to be greater than minus c. This is the function that satisfies this differential equation. Now, another very important thing about differential equation, and that's worth mentioning in the opening lesson, is how we classify differential equations. And this is going to... next time you'll probably understand better what I'm talking about today, because we're going to see the role those constants play in differential equations. So, if we have something like this, the third derivative of y plus the second derivative of y, I'm just coming up with this differential equation, minus, for example, 5y prime cube times x equals 0. And we have, for example, another differential equation, the second derivative of y squared plus y prime equals sine of x. Those are weird equations. It's not important the equation now, but some aspects of them. So here's a third. There is something called order of a differential equation. So order, and something called a degree. The degree is like the degree in normal equations, but for differential equations. So the order of a differential equation, it's the highest order derivative appearing in the equation. So for example, this is a third order differential equation because we have the third derivative of y with respect to x. So this is third order. This is a second order because we have y, the second derivative of y with respect to x. And there is something called degree of an equation. For example, this equation has, some y terms to the third power to the second power. Well, the degree of the equation is the degree of the highest derivative term in the equation. So, for example, highest order derivative term of the equation. So it might seem confusing, but it's very simple. Here we have y prime cubed, but we have the highest derivative, that is third order. So the degree of this equation is first degree, because the highest derivative term is just to the first power. The second equation, instead, we have a 2 here to the highest derivative. So this is a second order, second degree differential equation. So second degree. Now, you may say, okay, these are all definitions. We're just learning some of the jargon associated with them, but they are going to be useful in other lessons. So please remember this fact. Okay, so we discussed about general solutions, particular solutions. Now I want to tell you another story, and I'm going to use 2 examples. So we have, just to understand where those constants, where those degrees and orders of differential equations come from. So we have this example, y equals cx squared plus 3, or let's use another example that I think is better to understand what I'm talking about, 2 squared plus cx. Now, this is a function, it's not a differential equation. We want to turn it into a differential equation. Now you may say, we already have the function. Yes, of course, but we can generate differential equations by removing functions. What I mean by that is we want to get rid of this y. How can we do it? Well, let's take the derivative of the function with respect to x. We have 2 times 2 is 4, x plus c. Now we can isolate c, so c equals 2 y prime, that is dy by dx, minus 4x. We can replace c in this equation, so we have y equals to 2x squared plus c times x, so y prime x minus 4x squared. We can sum these 2 terms, so y equals to minus 2x squared plus y prime x, and we can rearrange the terms, so y prime x minus y minus 2x squared equals 0. And this is a differential equation. As you can see, we have a first degree differential equation. So by removing one constant, we got a first order differential equation. Now look at this function here. This is a more complicated example. So y equals c1x squared plus c2x plus c. Now we need to remove the 2 constants. So we're going to take the first derivative c1x, 2c1x plus c2, and this constant, let's use a number so we don't get confused, plus c2, and the second derivative equals to 2c1. We now know what c1 is. We can replace it in the first derivative equation, and we get y prime. We have the second derivative of y over 2 times 2, so second derivative of the function times x, and plus c2. So we also know what c2 equals to, because we only need to move this to the other side. So we have the first equation y equals to C1, so y prime over 2, sorry, y double prime over 2. Then we have x squared plus c2x, c2 equals to y prime, so y prime minus y double prime x, that multiplies x plus this 4 here. We can multiply everything by 2 and distribute the product, so this is what we get. We have, this is a plus 2y prime x minus y prime x squared plus 4 times 2 is 8. And we can even rearrange the equation, and but I'm not going to do it now. I want you to notice the order of these differential equations.